Okay, welcome everyone to this afternoon session. We are very happy to have Annegret Butcher from Radboud University here, and she will tell us about the volume of generalized tubes.
Thank you, Anna, for the introduction, and thanks a lot for the organizer for this nice workshop, and also for inviting me for being able to stay here a little bit longer. Yeah, I'm going to talk about a generalization of Weyl's tube formula. And in a sense, it's a kind of a transition now that we've heard a lot of talks about Riemannian manifolds from the Riemannian to the Lorentzian picture. So I'm trying to take a result in Riemannian geometry that first generalize in the Riemannian setting and then try to carry it over to the Lorentzian setting. So just for a question, who has heard about Weyl's tube formula before? Please raise your hand. Okay, well, at least some people, that's good. So my talk is structured as follows. So first, I'm going to talk about the classical setting. So, well, I'm going to. It's basically Weyl's result. So I would call this a spherical tube formula, and this is basically so everything critical that happens is in 4 dimensions for surfaces in R4 basically. So it's very, very basic and very, very classical. So we're going to consider cross sections in the normal space of this surface, and in the spherical tube formula we're going to consider balls. And the ball should be, well, could be in n dimension, and then the submanifold is embedded in Rm plus n. M is the dimension of the manifold, and n is the codimension. Then, well, in the second part, I'm going to sketch a proof of this result so that we understand why and how we can generalize this. So this is basically just a proof then, or a sketch of the proof. And then the third part, I'm going to generalize these cross sections that we're going to consider. So we're not going to considering balls, we're going to consider more general shapes and see whether the tube formula still holds. I mean, I haven't yet told you what the tube formula is, but I'll come in a second. So I'll call this generalized tube formula. And instead of balls, we're going to consider some polytopes. Well, I'm just going to, well, you can, well, if you want to consider icosahedron or something like that, I mean, cannot draw this very well, but, and then this is again going to be in Rm plus n. And then in the third part, I want to take this over to the Lorentzian setting. And actually, the reason for why I considered this problem is because I saw in a paper that said that, well, obviously you can't do the tube formula in semi-Riemannian geometry because the volume would be infinite. And then I said, well, who's going to take the area underneath the hyperbolite? Of course, you're going to take causal diamonds, right? And well, that was the idea for that paper. And you're going to see whether that worked or not. So in the Lorentzian setting, we're going to consider what I call the causal tube formula. And that actually is taking causal diamonds. And I will define this precisely later. And the interesting case, as I said, already occurs in dimension 4. So basically R3, 1. So that's basically the outline of the talk. And I'm just going to start with the very classical result and explain you what that says and how it comes about to be. So that's my next. So this is what's known as Weyl's tube formula. Yeah, and I should say that this joint work with my colleague Herr Teckmann. And he's actually, yeah, he's a fan of Weyl. That was easy to convince him to look at this problem. He also knows a lot about group theory. That's why these polytopes show up here. And he also had the same idea as me. He said, well, of course, these causal diamonds, their volume is invariant under Lorentz transformations. Of course, it should work, right? So that's why we considered the problem, because we both thought, well, it's kind of obvious it should work. So okay, what's Weyl's tube formula? Well, the basic setting actually was first considered by Hotelling. I think it was in an American Journal of Math in 39. And what he did, he looked at curves. Actually, he looked at a problem in statistics, so it had some applications. But he actually looked at the curve in Rn, or now in R3 or in R2, and spherical tubes around it. So like that. And so I kind of used this notation C plus A Bn. So this should be kind of the tube. It's a kind of a misuse of a notation, but I think you understand what it means. So we just go radius A, and then we consider the volume of this tube. And if this is like the length of the curve of this section, then you would say that, well, roughly the area, the volume of that tube should be something roughly like the length of that curve, or that section of the curve, times the volume of that cross section. And that's then, of course, well, a to the power n times the unit ball. So that's the first guess, right? And what Hotelling showed is actually, well, you don't have to do approximately, it's actually equal, okay? And apparently he presented that result in Princeton, and Weyl was in the audience, and he immediately generalized this result to not curves, but submanifolds in Rn, and m plus n. And actually his result also appeared in the American Journal of Math back to back with Hotelling's result, so it's super quick now. So that's the first result, and then Weyl's result is the following. Now it's gonna, that's why you need R4 actually, because hypersurfaces are already too special in a sense in 3 dimensions. So why Weyl? So Weyl considered an m-dimensional, well, connected, compact, whatever you want, submanifold in Rm plus n. So kind of use this plus notation. It's kind of easier to remember what is the dimension and codimension. And again, we're going to consider spherical tubes around this this submanifold. And as I said, you can always think about, well, it's best to think about surfaces in R4 if you want to have a picture. And so what he showed is the following. I'm just going to write it down. Theorem of Weyl is that the volume of this tube is now the following. Of course, the parameter A has to be small, right? Otherwise, you're going to have self-intersections. Is, again, the volume of the unit ball. And then you have a sum from D equals 0 to M, where D is even. And then a to the power n plus d divided by some n plus 2, n plus 4, up to n plus d, if d is even, and some term kd of m. And well, that was his formula. And now we're going to discuss what's special about this formula. So the first thing that you notice, well, it's a polynomial in A, okay? And it only has, well, not even, it could depends on the codimension also, but it only has like, it depends, only every second term appears. And then we have this kind of quantity here, the kd of m. In this case, that quantity was just the length of the curve. No? But in more general, these are some integrals. So hd ds. I'm not going to be very specific about how they look because they're very ugly. But the important thing is they are built up of coefficients of the Riemann tensor. So there are all kinds of variations, some products and sums. Well, not that complicated, but too complicated to derive it. But the important point is it's intrinsic, okay? So these are intrinsic coefficients. So they're just some kind of products and sums of Riemann tensor components.
But not
yeah.
the Riemanns, right? Just
no, the Riemann tensor, yeah, second, yeah.
Okay.
Yeah. I mean, because we are, the background is in a sense Rn. So it's easier, yeah. And then, okay, let's just look at some special components. So one essentially we already wrote down, K naught. K naught is just a volume, okay? So that's just integrating one. ds, I'm considering that to be the induced volume element of the Riemann of the surface. Then we have K2, and that's 1/2 times the integral over the scalar curvature. Also nice. And then, of course, you can have, like, depending on your dimension, you have more. And then if your manifold is closed and even, something special happens, and you may already see that in that case. But so D even and M closed is Kd M is actually 2 pi to the power. M. Is that correct? Oh yeah, M. M over 2. This S is a scalar curvature, yeah. Or sorry, what?
Yeah, the K2, the Invariance is scalar curvature.
Yeah, that's right. And you see that in that case, if, well, not D is not even, sorry. M is even, sorry about that. The dimension of the manifold is even, then the top coefficient is actually topological. It's not just a curvature invariant, it's a topological invariant. Okay, it's even more special. Okay, you can see it here. If M is 2, then you see it immediately from Gauss-Bonnet. And actually, this result of Weyl led Allendorfer and Weyl to the proof of the Gauss-Bonnet theorem in higher dimensions. So the first proof, not the standard proof, but the first proof, because of exactly that top coefficient. Okay, so this is this very special formula. It basically tells you it doesn't depend on how that manifold is embedded. The volume of the tube is always intrinsic. And it's not obvious that this should be the case. And I'm going to explain now, give now a kind of a short sketch of the proof of why this works. But I'm going to give the proof in low dimensions because otherwise I'm going to get myself messed up using this. Yeah. No, that doesn't matter. No.
What if then, if you embed, for example, the curve as a sort of vertical curve, and then the balls you're summing, but then you're saying you're summing the balls somehow transversely?
Well, it's always in the normal bundle. Yeah, it's always normal. Yeah, sorry. Yeah, I didn't draw it very well. Yeah, it's always in the normal bundle. Yeah, yeah. Okay, so this is it's an intrinsic quantity. Yeah. Yeah, because otherwise, if you have large A, I mean, you know, you don't want your tube to intersect itself, and that's why also you only can take embedded curves, right? You cannot take curves that self-intersect or anything like that. It wouldn't work. Sorry? Yeah. Yeah, sure. Because otherwise you have self-intersections, and then you would count some volume twice, and then, you know, that, yeah. No, that doesn't work. But in a sense, what you should also see from this formula, yeah, it's actually a local result. It's not, I'm kind of cutting it off, right? I'm not like adding the ends of it. So it's, and also the proof is local. And this, yeah. Sorry? Yeah, I mean, you know, if I would have like a curve that's just like that, I'm not like adding like a half sphere, a half ball here. No, I'm not. I'm kind of just looking at that.
formula is added.
No, but this is just how I draw it. No.
Is it because the curve is closed or something?
Well, the thing is, it depends how you look at it. You can consider it closed, then you don't need to worry about that problem at all. Yes. And if it's not closed, then you just, like, for example, if I'm in R2, I can have this curve, and I could imprint, I'm just considering this tube. I'm not adding this part here. This is not, it's not part.
When you see B of C plus B,
yeah, I know. This is an abuse of notation, I'm sorry. Yeah, I just wanted to not write it down too complicated. That's an abuse. That these two parts are never included. Yeah, but it's the easiest if you just consider the closed case, and then also this is true. Otherwise, of course, here would also have a boundary term otherwise. Yeah. Okay, so I'm going to give a sketch of the proof first. So, well, basically said that this is something that's already known. Hold on.
Similarly, I guess, for this formula to be exact for small a, you need the curve where the submanifold has some smoothness.
Yeah, it's all is smooth. Everything is smooth. Yeah. No, the non-smooth part is now going to happen in the normal section. Not the manifold will always be smooth. So actually, Alfred Gray wrote a whole book about tubes. If you're interested in that one, but mostly people did. They considered more general manifolds, made that less smooth, but the cross sections were always balls. And we're kind of doing the opposite. We're leaving the manifold smooth, and we're going to make the cross sections more rough. And the reason for that is exactly because we want to consider causal diamonds, which are not smooth. No? Okay, sketch of tube formula. So the tube formula basically has 3 parts, I would say. And the first part, after the first part, what Weyl wrote in his paper was, so far, we have done hardly more than what could have been accomplished by any student in a course of calculus. So the first step, is basically an exercise in calculus, but I'm still going to write down what the result is. I don't worry. Exercise. Yeah, if you need a problem, you may just going to consider that next time. So exercise in calculus. I didn't say that, Weyl actually wrote that in his paper. Okay, so what is that exercise going to give you? Well, of course, you're first going to just, so as I said, the formula is local, so we just assume that, well, we're doing everything local, and we have a parameterization of our manifold, and in the normal section, we have a normal frame. So basically, kind of write U is, well, some subset in Rm, sorry. Now I'm going to be careful. In Rm, and T is in Rn. Okay. Just going to always be careful about the M and the N. And the paper, we actually wrote it the other way around. So if anybody reads the paper, you may get totally confused now, but okay, actually here we are in, I'm already gonna consider a more general domain now for the first step, A of D, N in Rn. And for the moment, we're just gonna consider the ball. And so this is mapped to the tube if you want. Also, as Robert pointed out, of course, that's not completely correct to write it like that. I just do it. Anyway, oh. Here I have to write now, what did I do? Phi of U. So that gives me the point on the manifold. This is a local parameterization. And plus tk. And then I have n normal directions, so n normal unit normal vectors. And they're also normal, so I'm just, yeah. I'm going up to A, so T, the length of A is, T is less than A. Going in these normal directions. So this is orthonormal frame. For that point, well, n phi u of m. and this is of course then going to lie in this kind of a tube. Okay, so if A is sufficiently small so that you don't have self-intersections, then we can compute the volume as follows. So the first thing you do, you just you compute you need the Jacobian, so use Fubini of course, and then you see you need to compute the determinant of the two. Okay, oh, I said it, I didn't say that, but for simplicity, I'm gonna assume that that M is 2. Then I don't need to write that much, okay? Then I have n normal directions, and well, this is the Jacobian, and then you do a little bit of computation, the calculus exercise. And basically what you're going to do, you compute these derivatives and you bring in a second fundamental form in each of these normal directions, okay? So this is like second fundamental forms. How did I call them? The components are h, j, I, k, and the k is then relating to the nk normal vector. And then what you get is the following. A determinant of the identity, basically. Delta ji minus t, and t is now a vector in Rn, so inner product with the components of this second fundamental form. So the case vector goes in the case normal direction and case second fundamental form, so that's all works out. dt, and then what we also get is, well, the square root of the determinant of the gij's, and this is of course the u. This is just the volume element, so which I called ds before. Okay, so this is what you get from this exercise, and now we're going to look at that a little bit more carefully. What is it? So the important part here is this term. And you see that this actually, well, the h depends on u, right? That's outside. So it doesn't, for the inner interval, it's just some constants. So this is actually, and then you have the determinant of an, well, now I have to see. Okay, you have a determinant. The t has n directions, but because I assumed m to be 2, it's just a 2 times 2 matrix. And so this is a polynomial in t, okay, of degree 2, of degree m in general. So this is, I called it p of t, is a polynomial in Rn of degree m. And this is crucial for this is in a sense related to why you get a polynomial here, okay? And now I'm gonna have to delete something already, or not, yeah, no, I still have more space. Okay, so this is just a computation, and of course you have to do it carefully so that you get the right result, but no problem here. It's now in the second step where the real magic happens. Okay, so I'll call this the magical step. And the idea of this second step is the following. We are considering a ball, and the ball is invariant under the orthogonal group. But instead of considering now the domain, we're going to look at the polynomial, right? So we can look at invariant polynomials instead under this group. But at first, I'm just going to write down this polynomial to start with, and then we're going to see what remains after this integral. So as I said, the p of t is just a determinant, in this case 2 times 2. So I'm just going to write it down. T dot h11 minus t. Well, this is symmetric, but okay, this is how this determinant looks like. And then you can write it out, and I'm just going to do that now, because that's why I keep the dimension low, so that I can actually write down these things without too many indices. And then we get these terms where, well, the t appears twice, basically. And we're always using the Einstein summation convention, summing over the indices. Okay, let me just write this down, and then I will explain what happens. Okay. Okay, so this is what we would get. So as I said, a polynomial in t. And yeah, because we're still actually, I'm still actually considering the proof of the ball. Also, the first step I already wrote in more generality. If Bn is invariant under the orthogonal group, and so I could just multiply everything by a group by a rotation, and we could start the same integral, right? But instead, I could just average over the polynomial over the group, and so this is what we're going to do now to make it a little bit simpler. And I'm just going to write the average like that here now. So okay. Okay, what happens to these polynomial terms if I average? Oh, sorry, it's not completely straight. Okay, I average the t. Well, say the t1 gets cancelled with minus t1, so nothing remains, okay? So this is actually going to be 0. And if I do the averaging here, the only thing remains, the only invariant polynomial of degree 2 of the orthogonal group is, of course, the norm. So actually what I get here is just, well, now I only have 2, but okay. Generally t squared over m, and now just t squared over 2. Or maybe I should write m here. Well, okay. Or n, sorry, I'm getting confused with my indices here. No, it should be n, right? Because I have n. Yeah. No, that's right. Okay. So what actually remains after I do this averaging is 1 plus t squared over n h1 1 2 2 minus the mixed terms. Okay, already looks a little bit better, but we still have the extrinsic curvature here. I mean, I said the formula is intrinsic, but it's still extrinsic here. So what happens here? Well, this is something that's actually basically the theorema egregium, that's Gauss equation. This is intrinsic because the background is just Rn plus n. Okay, so this is in a sense the magic now. The theorema egregium maybe is a magic. So this is just now got R1, 2, 1, 2. And this is like, well, by convention, whatever convention you use, 1/2 the scalar curvature. Okay. This is why I did it in 2 dimensions, right? Otherwise, it will be super messy here at this point. Okay, so you see, that's all that we need to do. And now we basically have to do the step 1 in the other direction. Maybe I'm going to carry that out elsewhere. Well, now it's actually trivial, but I'm going to put it here. So now we have to just do the computation. So this is basically step 3, and this is just putting everything together that we have done before. So we'll take what we have from step. Now, of course, we did it for the ball, but it works similarly. Well, that step works similarly. The second step is the real problem. So we put 1 and 2 together. We compute the integral, which is now easy to do. And then what we get, well, in these 2 dimensions, omega n, a to the power n, the area. So now we're in 2 dimensions, the area of M plus omega n, a to the power n plus 2 over n plus 2. And then we would integrate the scalar curvature, but if we are assuming closed, then that's just, again, the Euler characteristic. So this is 2 pi of m. And so basically, I've shown the Weyl's tube formula in this simple case for surfaces. Okay. I kind of didn't do all the complicated stuff where a lot of mixed terms would show up, but you can find it in the paper. Yeah. For small a, yeah. For small a. Yeah. For small a. That's always assumed that we are doing analysis. We can do that. Okay, sorry.
If I just try to embed, let's say, S a constant curvature manifold, this sort of looks like.
You can do that. Yeah, there are a lot of generalizations, and actually already Hotelling and Weyl have both considered the sphere. So, and then in Gray's book, there's everything more general. You can do it in C, and you can do it in CPN. You can do whatever you want in Kähler manifolds. I mean.
Sort of just get a scalar curvature of the sphere. This looks like a Gauss sort of combination.
Yeah, this is the Gauss equation, basically.
Right.
Yeah.
So then would you get the difference in scalar curvatures between the sphere and.
Yeah, exactly. You would get something more non-trivial here. If it's not flat, you get some extra terms. Yeah. Yeah. Did you have a question?
I just wanted to understand what the question was there.
If you wouldn't be embedded, yeah.
Instead of our n.
Yeah, then there will be additional stuff here. Now it's basically 0 because our n is flat now. Yeah, but it's easy. Like already Weyl and Hotelling have done the sphere case. It's really not. And in the book you can read more, but I really don't even. I mean, we started with the simplest case, or we start with the most simple example. Okay, so well, basically we've now proved Weyl's tube formula for m dimension of m being 2. No? And the more general case you can read in our paper. In higher dimensions, you need the first fundamental theorem of invariant theory for that, because you need to make sure all these combinations cancel. You have diagonal actions and stuff. Okay. Okay, and so that's basically now I did that proof part. And of course, why I wrote this down is because we want to generalize this more complicated domains, not just the ball. And I wrote down the proof to show you, well, the first step and the third step are really just computations. There's nothing special going on. So if there's anything that you have to do, then it's in the second step, in the magical step. And we want to kind of consider cases when this second step still works in a more general setting. Okay. And what you see now, so this is now part 3, generalized tube formula. Still in the Riemannian setting. Generalized. So basically 1 and 3, they're not problems, there's just computation. And for the second step, you can slightly modify that. And what you need is basically that if you consider another domain, and that's a regular polytope, that is invariant under a certain subgroup of the orthogonal group, the polynomials up to degree, I have to think, up to degree m have to be the same. Then you can basically carry it over the proof as it is. Because then you can just, then basically, okay, so I'll write it here. If G is a subgroup of the orthogonal group such that the averages with respect to that group are the same as the averages with respect to the orthogonal group. Of course, if you want to have it for all degree polynomials, it will be just the orthogonal group. But we only need it up to degree m, right? Up to degree m. So if this is satisfied up to degree m, basically the same proof works and you get a generalized result for more general domains. I'm just going to write down, okay, so up to degree m, then tube formula works. But yeah, I'm going to write down explicitly what I mean here. Is it clear what I mean? So the averages are the same, and then basically just take the averages that I've already computed. And the only thing that changes in the step 3, of course, the integral will be a little bit more complicated because I'm not integrating over the ball, but over a more general domain. But the invariant property is not disturbed, no? That's the thing. Okay, well, maybe that I should leave. So I'm just going to write down the more general result that we obtained. Okay, the setting is otherwise pretty much the same. So MM, say a closed connected manifold, so compact is our boundary, submanifold of Rm plus n. The submanifold stays the same, and then we consider a domain Dn in the normal space, which is invariant under a subgroup of the orthogonal group. Well, we call it invariant under G, such that, and we call this condition orthogonal up to degree m. So this means that the polynomial invariants up to degree m are the same as the one of the orthogonal group. In higher degrees, anything else can happen, okay? And then the result is that the volume is still intrinsic, and the formula looks as follows. Zero to m. It's again a polynomial. The denominator is missing one term because we're not. So the last thing looks a bit different. Then we have integral of over dn, t to the power d, dt, and again times these invariants. So this is the sextant. So the only thing that really changes is this part here, no? And here's a term missing, but okay. And that you have to compare to this thing here, no? So in particular, it's intrinsic, okay? It's a bit more complicated to compute, but it's still intrinsic. And just to illustrate like what this means, I'm going to give you some examples. Yeah. Yeah, exactly. It's exactly the same. Yeah. I mean, something that I didn't write down, like the integral of the scalar curvature. Okay, so I'm just going to give you some examples now, how such domains would look like. But the basic takeaway message is, the smaller the group, the more invariance it has of polynomials, no? And the harder it is to satisfy this condition. Okay. So for the examples, we do two things. We first keep the codimension fixed, and then we keep the dimension fixed, and we see what happens. Okay, so if codimension of M is n is 2, so we keep this fixed now. Then we can, for example, consider a dihedral group. And you see that if M is less or equal to 3, so the dimension of the manifold is less or equal to 3, you can use a square, and you'll still get an intrinsic formula. And then you can go, for example, to M less or equal to 5. You can use a hexagon. Okay, I guess you kind of see what happens. If you let M go to infinity, you're gonna get a ball, no? It becomes rounder and rounder. So this is what happens if you leave the codimension fixed. And why? I'll put it here. And now what we're gonna do is we keep the dimension fixed. So ultimately, as I said, the most interesting will be case to study surfaces in R4. But just to qualitatively understand what's happening here, no? Okay, so this is also more demanding to draw now. So now we do the dimension of M, which is M, and we keep that fixed. So we always consider a surface, but we do that possibly in higher dimensions. Okay, now it becomes complicated. So in R2 plus n, now it becomes difficult to draw. Okay, let's start with n equals 1. Which is an interval basically minus 1, 1. Okay. Hypersurfaces, the formula works for hypersurfaces. That's actually just like the curve. That's basically the trivial case. So that works for all M actually. No problem. Then if we go to n equals 2, I mean, that case we already had, we can use a square or as a Lorentzian geometry would say, a diamond. Okay, and so when can you use a diamond? Up to which dimension can you use a diamond? Well, you can use it in dimension 2, but you can actually also use it in dimension 3, and I've already written this down. So this is if M is less or equal to 3. So here you can actually say for all M this works. Okay. Okay, then if we go to higher codimensions, there are essentially several ways of generalizing this shape. So the first one is to consider a hyperoctahedron. So this I can still draw that. Something like that. Okay, hyperoctahedron. And that has a symmetric group with this symbol Bn generally. And it has a second fundamental, it has a second, so this group has a second fundamental degree of 4. And we have actually shown in our paper also that if you have one less degree than the second fundamental degree, which would be the next invariant polynomial, which you don't want, then it still works. So this hyperoctahedron works up to, for all M less or equal to 3. You can use a hyperoctahedron. So, however, we are kind of interested in the causal tube, so this is not the kind of...
Quick question. Is hyperoctahedron is just a ball in L1 norm, or what is hyperoctahedron?
Yeah, it's like a cube, but turned. I mean, yeah.
Is it the
It's
ball
like
in L1 norm on Rn? Is that the one?
That should be, yeah, right, yeah.
Okay, thanks.
Yeah, I could just say here this is a square and this is a cube. But in higher dimensions, I don't know. Okay, so then what we're actually interested in is the causal tube. So we would actually like to consider something like that, right? And well, I would call this the diamond, call it like that. And this has a symmetry group is On minus 1 times O1. This is actually worse. So in dimension 2, in dimension greater 3 or more, you cannot use that. This is the 2-dimensional version, but this one you cannot use. It has less symmetries than the hyperoctahedron. So this is actually only works for M. Well, M equals 1 actually. So this is actually not working out here, even in the Riemannian case, okay? Because the invariant polynomials here are T1 squared up to T n minus 1 squared and Tn squared, and of course these polynomials are not invariant under orthogonal group, so that's already not working. Okay, and then well, other generalizations would be, for example, the icosahedron or dodecahedron. You can also consider it to be the soccer ball. Then I don't have to draw it, okay? It's a truncated icosahedron. So the soccer ball, if you have 3 codimensions, you can use a soccer ball, and then that's good up to dimension of m less or equal to 5. And how do I know that all this works? Well, this is already computed by several people. If you know the groups under which these polytopes are invariant, then you can actually read this off in some table in a book. So this is what we know, and just for fun, I'm going to give one more example before I go to the causal tube, and that's I call this the Fields tube. Well, maybe I'm just going to write it there. Because as we all know, or maybe I hope you have seen it, there's this kind of nice regular polytope hanging out there, actually a polytope in R4 projected to R3. So just to appreciate that, I will tell you for which dimensions you can use that to get an intrinsic tube formula. Okay. So this is this polytope hanging out there is the 120 cell. It has also a more complicated Greek name that I always forget, so let's just call it like that. It consists of a lot of pentagons. This is a regular polytope in dimension 4.
You're only calling it Fields tube because it's only blue, right?
Yeah, I'm just calling it like that. This is like I just gave it the name. That's right. It should be called the Coxeter tube. Yeah, I also considered that, but maybe that's that's right. I mean, all of this goes back to Coxeter in a sense. Yeah. Okay, so what did I write down here? Okay, so it has a symmetry group with a symbol, with a Coxeter symbol H4. So H4 is this Coxeter symbol. And you can read it off in a table that it has this second fundamental degree of 12. And as I said, this will be so that the next invariant polynomial would have degree 12, but we don't want that, right? We want to have the same ones as the orthogonal group. So we can only go up to dimension 11. So, so tube formula, intrinsic for m less or equal to 11. Okay, so you can actually do this is in 4-dimensional. Now you can do this in 15 dimensions with the 120 cell. That's just for fun. I mean, I'm not sure if anybody's gonna use that. Okay, but now let's yeah, I don't have much time left, but let me just say now what happens in the causal tube. So that's kind of fine, depends on the invariance of the group, invariance of the domain. And the causal tube, I already showed you, it's kind of problematic if you use higher codimensions. So you want to actually stick to the dimension 2 case, but that's not a problem because physically we are in 4 dimensions anyway, and the only non-trivial case is surfaces in R3, 1. And for surfaces, for curves and hypersurfaces, the tube volume still works also in R3, 1. And the basic idea in the basic idea for the causal tube would be that you are in a domain so you go like 1 in the normal direction. So you do this for M, a space-like surface. Then you have a time-like direction in the normal. Then you draw the causal diamond. That will be the domain that we're considering. The volume of that domain is invariant under the Lorentz group, yeah. That already makes it look good. However, it turned out it doesn't work, and the reason is, of course, that the invariants of the Lorentz group are different than the invariant of the orthogonal group. Like the Lorentz group is not a subgroup of the orthogonal group. Okay, so if I write it like that, so well, if this is the group, then the invariance the invariants are only the same up to degree 1. So but to work for surfaces, we would need them to be invariant up to degree 2. So actually, the tube formula is false in the non-trivial case in R3, 1. Okay.